Yeah. Yeah. So in case you don't know me, I'm Ziming. I'm now a fourth year PhD student at MIT, working with Professor Max Tegmark. My research interests center around AI plus science. So it can go both ways. Either you develop better AIs for science, like AI scientist, or you use inspirations or like tools in science to enhance the improvement of AI. So like this work is like both ways. We first try to use some ideas from math and see if we can develop new AI tools and see if we can whether these new AI tools can give something back to science. Yeah, so this is about our recent work called the Kolmogorov-Arnold networks. Swipe the camera. Yeah. So today's AI is built upon this new math. Sorry, today's AI is built upon this math theorem called the universal approximation theorem, which basically says that a high dimensional function, you can decompose a high dimensional function into a linear combination of some nonlinear features with this nonlinear function sigma, which is basically just this two-layer network known as the multi-layer perceptron. But you can make it deeper. That's why it got the name multi-layer. But we are asking this question: are there any alternative theorems we can use? We can leverage these new theorems. Well, not necessarily new in the mathematical sense, but like in the AI world, to build another AI skyscraper based on new building blocks. So here we're examining this theorem called the Kolmogorov-Arnold representation theorem. First question, what is the Ka representation theorem? It says, again, like given a high dimensional function, you can write it down as a finite composition of one-dimensional continuous functions and just the summing operation. So more concretely, you can write down an n-dimensional function in this form, where you have the outer functions capital phi q and the inner functions phi qp. They are just one-dimensional functions, and they are finite. like the number of these functions is depending on the number of inputs variables n here. So what's nice about this theorem is that it tells us that the only true multivariate functions is the sum. Like you can express, say, multiplication with just the summing operation plus some 1D activation functions. So that sounds like really great news for approximating high dimension functions, especially for machine learning, because in high dimensions, to learn high dimensional functions, we know we have cursive dimensionality. But this theorem seems to tell us that you can decompose high dimensional functions into one-dimensional functions, which do not suffer from cursive dimensionality, which are great. But immediately there is this plot twist. Back in 1989, Professor Gerossi and Paggio, they they wrote this paper examining the relevance of Kolmogorov's theorem in the context of learning, and they conclude that we review Kolmogorov's theorem and show that it is irrelevant in the context of networks for learning. So that seemed so this paper basically sentenced the Ka theorem to death. Well, at least sentenced to jail for like 30 years. So is that the end? Is that the end of the story? Well, we want to tell you that that's not the end of the story, and there's again a plot twist. So let's try to see what they say in their paper, why they sentenced the theorem to jail. So their argument was that the theorem fails to be true when the inner functions are required to be smooth. Basically, the original theorem says that you can decompose like a high-dimensional continuous function into 1D continuous functions, but it doesn't guarantee you to decompose it into 1D smooth functions. But to learn something like with gradient descent, you would need the functions to be smooth. Only being continuous is not enough. Like even with continuous functions, you can still have some really pathological behavior. You don't have like the smoothness constraint. So that's basically the argument, because the theory does not tell you anything about the smoothness of the functions, but in practice, only smooth functions are feasible in practice. So one thing, one interesting word they use is that a stable and usable exact representations seems hopeless. So that's like the attacking point that we want to like we want, that's the angle we're taking. Maybe we do not need exact representations. Sometimes approximate representations might suffice. So their paper was theoretically sound. Oh, was sound theoretically, but I'm trained as a physics student, so my level of rigor is lower than mathematicians. So me and also Max, we tend to have lower bar of being rigorous. So we have this naive optimism. Firstly, maybe like empirically, maybe we don't care about exact representation. Sometimes approximate ones may suffice. As long as it has some level of explainability or interpretability, that's fine. And secondly, a common wisdom in modern deep learning is just stacking more layers to get deeper networks. They are basically arguing against the two-layer Kolmogorov network. But what about we build deeper networks? Maybe for deeper networks, even under the smooth constraint, you can win the expressive power back. Lastly, just the can-do spirit. We cannot say something doesn't work before really building it with the state-of-the-art techniques. They have the negative claim back like 30 years ago. Back then they didn't even have the back propagation. Like it was not popularized back then. So we want to take everything we have in the modern area of deep learning and see like how far we can go. So that's the mindset. So just with the can-do spirits, we propose, or more properly, we rediscover or we contextualize the idea of Kolmogorov networks in today's deep learning world. So here's the overview. First, I will introduce the math foundation. Well, I already briefly mentioned it. I won't dig deeper into it, but just I will emphasize again like the mathematical beauty of it, and then I will talk about the properties of cans, why and in what scenarios cans are more accurate and interpretable than current deep learning models. So first the math foundation, I already covered this part, but I want to emphasize again that the theorem looks really nice. That allows you to decompose a high dimensional functions into one-dimensional functions. And after the decomposition is done, your only job would be just approximating the 1D functions. So that's the idea of the Kolmogorov-Arnold networks, like decomposition first and then learn the 1D functions. Well, yeah, so this representation looks a bit complicated. You see that there are this big summation symbol, and you have two layers of composition, and this looks complicated, but don't worry about it. It's just equivalent to this two-layer network. Let's suppose we have two inputs, x1 and x2, and we have the outputs at the top here. So the representation in the original theorem is basically just that you have 5 hidden neurons in the middle, and to get the activations in each hidden neuron, you basically apply 1D possibly nonlinear function to x1 and x2 and sum up these two nonlinear activations and to get the activations at a node. And in the second layer, it's similar that you apply some nonlinear function to the hidden activations, summing everything up at the output node, and that's how you get the output. So the computation graph is it's super clear with just this this diagram, and this might be remind you a lot of this looks just like a multi-layer perceptrons or fully connected networks where everything just fully connected, but instead of having activation functions on the nodes, now we are having activation functions on the edges. And on the nodes, you simply just have the summation operation, which is really simple. Yeah, just to make it more elegant and beautiful, we can more intuitive. We can basically, because like 1D functions, we can basically just visualize them with 1D curves with the x as the input and y as the output. So now a CAN network is basically you can picture it as this, and by staring at it, you can have some idea what's happening inside. Yeah, so I mentioned this is just so the theorem, so the representation is equivalent to a 2-layer network, but can we go deeper? The answer is yes. Algorithmically speaking, because it's just a stack of 2 layers, which from which we can abstract a notion called the CAN layer. So the original 2-layer network is basically a stack of two CAN layers. And for each CAN layer, it's basically just taking some number of inputs and outputs some number of outputs, and in between is fully connected. And on each edge, you have some nonlinear learnable nonlinear activation function. And in the end, and in the output, you summing up the incoming activations. That's how a CAN layer works. And you can simply stack more and more CAN layers to get deeper and deeper CANs. This is just a 3-layer CAN. Like the first layer, you're taking 2, output 3. The second layer, you input 2, output 3, and the last layer, you input 3, output 1. So this is a 3-layer network which approximates a scalar function in 2 dimensions. But obviously, you can easily extend it to arbitrary dimension, like arbitrary input, arbitrary output, arbitrary width, arbitrary depth. So you have all the flexibility to choose the size of the network. Yeah, the first question Professor Poggio asked me when I presented this network to him, he asked, is that why do you need these deep networks? Because the original theorem told you that you only need the 2-layer constructions. And here's just a quick answer that I can give you an example. So please look at this symbolic formula. And if you examine it, you would immediately realize that you would need at least 3 compositions to do this, to construct this formula. You need the squared function, you need the sine function, you need the exponential function. There are because it's the compositional structure, they're in different layers. So you would at least need 3 layers to learn this formula. And indeed, if you just use a 2-layer network, the activation functions becomes really oscillatory, becomes really pathological, and the performance is bad, and also the interpretability is bad. But in the right, I show that a 3-layer network, a 3-layer CAN trained on this data set, and after training, you would immediately see the learned activation functions. In the first layer, you got the squared. In the second layer, you got the sine, and the last layer, you got the exponential. Well, you may think this is some other functions, maybe just some local quadratic, but yeah. But you can like do the template matching with the candidate functions and figure out which one fits the best. Yeah, so I said that these activation functions are learnable. How do we make them learnable? Because they're functions. And the common wisdom is that we need to parameterize the things to be learned so that we can use gradient descent to learn to learn this stuff. So the idea is that we parameterize a 1D function with B-splines. So B-splines is basically some piecewise, some local piecewise polynomial functions. So here I showed that there are some local B-spline bases, and the way we construct the activation functions is by linearly combining this B-spline functions, and the only learnable parameters are just the linear coefficients of this local basis. And what's nice about this formulation is that we inherit the advantage of B-splines. We can easily switch between fine-grained grids and coarse-grained grids. If you want something to be more accurate, you can choose the mesh to be more fine-grained. If you want the model to be smaller, so you can have a faster inference, you can choose a more coarse-grained model. Yeah, that's basically the idea of CANs, and we can compare MLPs and CANs side by side because they do share some similarities, but also share some but also have some differences. So MLPs are inspired by the universal approximation theorem. CANs, again, inspired by the Kolmogorov-Arnold representation theorem. The networks looks a bit similar in the sense that they're both fully connected, but they're dual. They're different, but they're dual in the sense that MLPs have fixed activation functions on nodes. Well, you can make them trainable, but they're on nodes for sure. And in MLPs, you have learnable linear weights on edges. By contrast, CANs have learnable activation functions on edges, while CANs have this simple linear summation operation on nodes. So in this sense, CANs does not separate the linear part and the nonlinear part as MLPs do, but it integrates both the linear part and nonlinear part altogether into the CAN layer. And the CAN network is simply just the stack of the CAN layers. Yeah, so in both cases, you are free to stack the model to become deeper and deeper because you have the basic notion of a layer. You just stack more layers to get the deeper networks. Yeah, so that's the basic ideas of CANs, and now I want to elaborate more what are why do we care about this? What are the advantages that CANs can bring to us, but other black box models do not bring to us? So the first property is the scaling behavior of CANs. As I mentioned before, the idea of CANs is decomposing high-dimensional functions into one-dimensional functions. So that looks like really promising. That it can get us out of the curse of dimensionality. Let's suppose we are trying to approximate a d-dimensional functions, and suppose the function has no structure at all. So then we need to have a hypercube and have a uniform grid on the hypercube. Let's suppose we have 10 anchor points along each dimension. Then you will need 10 to the power of d number of anchor points in the d-dimensional hypercube. So that's exponentially expansive. So if you do the classical approximation theory, you would notice that the approximation error would decay as a power law, as a function of the number of input dimensionality, and the exponent is 1 over d, meaning that you got exponentially slower when you have more and more dimensions. Like if you need 10 points in 1D, you would need 100 points in 2D, you would need 1,000 points in 3D, and so on. But if the function has some structure, like if it has the Kolmogorov-Arnold representation, then we can decompose it into a bunch of 1D functions. And then our job would just be approximating 1D functions. So now effectively D becomes 1. So you got the fastest possible scaling laws. But the caveats, immediately the caveat is that the assumption is that we like the function has a smooth finite size Kolmogorov-Arnold representation. All of this, all of these adjectives like smooth or finite size are just practical conditions for a network which we have access in practice that can really learn the network. We want it to be smooth because we parameterize it with B-splines, which are smooth. We want them to be finite size because for sure we cannot deal with an infinite size neural network. So yeah, so we just did some sanity check on some symbolic formulas. So yeah, so symbolic formulas are like widely used in science, so that's why we test them first. So let's see. So the red dashed line is the theoretical prediction. Here we are using cubic spline, so k is 3, and the scaling exponent is k plus 1 equals 4. And the CAN network, the curve, yeah. So the thick blue line is for the CAN network, and you see that almost like the empirical results for the CAN network almost agrees with the theoretical prediction, although sometimes perform slightly worse. Or in this case, in the second to last case, it's a 100-dimensional case, and it performs much worse than a theoretical prediction because of because the dimension is just too high, and the network can get stuck at some local minima or whatever. But nevertheless, it still outperforms MLPs, which you see up in the upper right corner here. Like decay is really slow, but CANs at least can outperform MLPs to a great margin, although still not saturating the theoretical prediction. But still, the scaling law that CAN shows looks promising. That it seems to not fully beat the curse of dimensionality, but at least partially beat the curse of dimensionality. Well, yeah. So, yeah, just to play the devil's advocate here, you may immediately notice that I'm on purpose just deliberately using this symbolic formulas. You might be wondering, well, maybe the functions we care we encounter a lot in nature may not be symbolic. They might be some weird, like at least for special functions, they are like infinite series, which are hard to be represented with just the finite network. So what's the CAN's performance in that scenario? So yeah, so we just tried some special functions, which we know for most of them, they do not have analytical formulas. And indeed, we see that the scaling laws of CANs do not saturate the theoretical prediction, meaning that probably you cannot decompose like a high-dimensional functions into just a 1D functions. But still, our goal here is to outcompete MLPs, and it's a feature, not a bug. Like not all the functions can be decomposed into smooth finite representations of this Ka representation. They may admit non-smooth finite size or smooth infinite size, but neither case is what's accessible in practice. So here we show that in most cases we can achieve this -2 scaling law, which means that the CAN network sorry. So here these special functions are all just two-dimensional. These according to the spline theory, it would predict a two-dimensional. It would predict a two-dimension, like a scaling exponent to be 2, which agrees with the CAN results. But in some case, we can still got the -4 scaling law, and the reason is that actually this is secretly although we call it a special function, spherical harmonics are not that special in the sense that they're still decomposable. So you can get the -4 scaling, but also in other cases you got some worse behavior. Like you got the -1 scaling, which means that the can is underperforming, even out underperforming compared to like the spline theory. But what's interesting is that in this case, MLPs are even more underperforming than CANs. So this may tell us that maybe for low dimensional problems, neural networks are not that necessary, and even the spline theory, like the spline approximation, can outcompete the neural network. So it's something to be think about. It's something good to keep in mind, because neural networks just have too many degrees of freedom and may have optimization issue. Yeah, so beyond function approximation, we can go on to solving partial differential equations. So in the setup of physics informed learning, basically we're trying to solve, we're basically trying to represent the solution of a PDE with a MLP or with a CAN network. So the only difference from the previous results, from the previous experiment, is that we're using the physics informed loss rather than the regression loss. So the optimization becomes more complicated, but still it's just approximating some function. Yeah, so we still see that with CANs we can get this optimal scaling law, while with MLPs you see that it has the scaling law at first, but it plateaus really fast, and then it does not improve when you have more parameters beyond 10,000. Besides being more accurate, we can also gain some insight what the network is learning. So for this example, we can for this PD example, we can actually visualize the CAN network like this, and immediately you can see that there's some like sine waves and there's some linear functions, and you can even do symbolic regression to it, like our software provides you a way to do this. You can do symbolic regression to it, and after you do this, you can do some further training, and you can even extract out the symbolic formula, which gives you like a loss down to machine precision. This is something that standard neural networks would not give you because they usually you cannot convert a neural network into a symbolic formula very easily, but with CANs, you can easily do that. Yeah, another property of CANs is that it has this property of continual learning, at least in 1D. So people have found that this claim might be invalid for high dimensions, so take my word with a grain of salt. But at least for 1D, the case is like we want to approximate this 1D functions with 5 peaks, but instead of feeding all the data at once to the network, we're feeding each time we just feed 1 peak to the network. And we do the sequential learning. At each stage, the network is just fed with just 1 peak. And with CANs, because we are using the local B splines, so when it sees the new data, it does not update the parameters correspond to the old data. So it has this, it can get rid of this catastrophic forgetting. Like when new data are coming in, the CAN is able to memorize the old data and still do quite well on the old data. But this is not true for MLPs. Like when the MLPs are fed with the new data, they catastrophically forget about the old data. Because in MLPs, you usually have this global activation functions like the Silu functions or ReLU functions. So whenever you make adjustments locally, it will affect the predictions far away. So that's the reason why MLPs would not keep would catastrophically forget about the old data. Yeah, so that's the first part about accuracy. The second part is about interpretability. You might already have some sense because we are able to visualize the network as a diagram. So the hope is that you can just stare at a diagram and gain some insight what's happening inside the neural network. Yes, yeah. So here we have some um some toy examples of, yeah, for example, how do cans do the multiplication computation. So we have x and y as the input and the x times y as the output. So when we train the CAN network, we also have something similar to L1 regularization to sparsify the network. So we can extract out the minimal network to do the task. So in the multiplication case, we see that only two neurons are active in the end, and we can read off the symbolic formulas of how and get a sense of how it does the computation. Well, I marked the symbolic formulas here. It may take a while. Uh, it may take a while, but but the point is that it basically just some squared functions, and the way the CAN network learns to compute this multiplication is by leveraging some squared equality here. And the second example, the CAN is tasked with the division task, where we input two positive numbers, x and y, and CAN is asked to predict the x divided by y. And because here x and y's are both positive, the CAN network learns to first take the logarithm transformation and then take the subtract the two logarithm and then transform the thing back via the exponentiation. So that's really cute. One example of the Kolmogorov theorem is that you can basically do the multiplication of positive numbers or the division of positive numbers in the logarithmic scale, because because the division or multiplication in the logarithmic scale it would translate to like addition and subtraction in the logarithmic scale. Yeah, so these examples are really simple. You might be wondering, what about a more complicated formula? Then it might be very complicated to decode what the cans have learned. So I would want to argue that this might be a feature, not a bug, or you can call it a bug, but I will call it a feature, in the sense that sorry, I didn't show the network here, but let's suppose we're doing this formula here, like u plus v divided by 1 plus uv. So if you're familiar with relativity, special relativity, you will realize that this is the relativistic velocity addition. So at first, I thought that I need a 5-layer CAN to fit this function, because you would need multiplication, which would consume 2 layers. You would two additions consume another 2 layers, and also you would need the division. So that's in total 5 layers. But it turned out you can just use a 2-layer CAN to fit this function perfectly well. And in the end, I realized that this is just the rapidity trick known in special relativity, where you first do the arctange transformation to u and v separately, sum the thing to rapidity up, and then you do the tangent transformation back to get this formula. So in this sense, it's rediscovering the rapidity trick, well known in the special relativity. And in some cases, I indeed find that the network finds some more compressed, compact representation than I would expect. That's good news in the sense that in the sense that the network is discovering something more compact. So the representation is more powerful than I have expected. But the bad news is that sometimes the interpretation can be subtle, can be a bit more complicated. But I mean, it can be a feature or bug depending on your view. Yeah. So this is one paragraph I take from the paper. This is criticized. Has been criticized a lot in the social media, but I find this analogy really interesting. So I still want to highlight this part. So to me, I think Can is like it's sort of like a language model, or like a language, or even like language for AI plus science. The reason why language models are so transformative and powerful is because they are useful to anyone who can speak natural language. But the language of science is functions, or more advanced mathematical objects built on functions, because cans are composed of functions which are 1D, so they are interpretable. So when a human user stares at a can, it's like communicating it with the using the language of functions. So to elaborate more and to make it more entertaining, let's suppose we are, like, my advisor Max is communicating with the CAN network. Here, I picture the CAN network as a trisolarian from the three-body problem. I'm not sure if you guys have watched it, but basically the trisolarians, their brains are transparent, so they cannot hide any secret from others. So they are totally transparent. So so Max went up, give the can a data set. Max was like, here is my data set. It contains the mystery of the universe. I want you, the can network, to figure out the structure of the data set. And the can initialize the can network like this. So here's the brain of the can network initially. And Max, given the data set, Max wants to train the CAN network, to train the brain. And after training, you can get this sparse network, which you start to see some structure. But still, there's still some residual connections, which looks quite annoying. So Max asked the CAN network to prune the redundant connections. And after pruning, you got this subnetwork, which is responsible for the computation. And Max further asked the CAN network to symbolify it, because it looks like in the bottom left, it looks like just a sine function. And in the bottom right, this looks just like a parabola, and this just looks like an exponential. So maybe you can symbolify it to gain some more insight. So yes, so the CAN network said, yes, I can symbolify it, and you can, and now the data set goes all the way down to this symbolic formula. But we can imagine another conversation Max would have with an MLP. So Max went up and gave the data set to MLP and want the MLP to figure out the symbolic formula in it. And like before, the MLP initialized the brain, looked like something like this, really messy. After training, Max asked MLP to train the brain, but even after training, the connection still looks really messy. And MLPs were like, and the MLP is like, I really trained it, but the loss is pretty low, but it's just that the connections are still very complicated. Now Max got confused, like what's going on? What's going on with your brain? And now MLP is like, it's just that you humans are too stupid to understand my computations. You cannot say I'm wrong simply because you cannot understand me. So Max now got really pissed off and turned back to Kans. Right. So those are just some imaginary stories I made up with the sympathetic example, and that sympathetic example is really simple, but I want to show that we can really use CANs as a collaborator in scientific research, and CANs can give us some non-trivial results. Can give us some new discoveries. So the first example is yeah. So this example was used in a DeepMind Nature paper 3 years ago, where they used an MLP to discover a relations in the knot data set. So each knot has some invariance. Basically, each knot is associated to some numbers, and these numbers, they have some relations, and we want to dig out the relations among these variables. So what the DeepMind people did was they trained an MLP and used the attribution methods, basically take the gradient with respect to these input variables and and use that as a score to attribute these features. And then rank these features to get a sense of which features are more important than other features. And they identified 3 important features. That's the only thing that's automated in their framework. And then the human scientists came in and trying to come up with like a symbolic formula for it. So we're asking this question: can we rediscover these results with more automation, with less, effort, and probably even discovering something new that the DeepMind paper were missing? So first, we are able to discover the 3 important variables with the CAN network with much more intuition and automation. So their network, they use a 5-layer MLP, and each hidden layer have 300 neurons. So that's really hard to interpret. That's why they use the feature attribution. But we find that surprisingly, we only needed one hidden layer and one hidden neuron, the CAN network, to do the task as well as their 5-layer, like a million parameter MLPs. And with this, you can also clearly see like the activations. The importance now basically becomes you can basically understand the importance of these variables with the like the L1 norm of these activation functions. So that's also how we visualize the connections. So you can basically read off from this diagram that the strong connections are the important variables, while this weaker or even nearly transparent connections, meaning that irrelevant variables. Yeah, we can also discover symbolic formulas, as I said before, because the CAN network decomposed high-dimensional functions into 1D, and then we can just do template matching in 1D to see what each 1D functions represent symbolic formulas, and then compose all these 1D functions back to get these high-dimensional functions. Something beyond their paper we discovered is that their setup is a supervised learning setup. Basically, they need to partition the variables into inputs and outputs, and they use the inputs to predict the outputs. But in some cases, we do not know how to partition the inputs and outputs. All the variables, they are equally they are treated equally. So we want to develop this unsupervised setup where all the variables they serve as inputs, but we use some notion of contrastive learning to classify whether some given input is a real knot or a fake knot. Well, that might be too technical, but the result is that we are able to discover more relations beyond the relation they discovered, because they manually partition one variable as the output, so they can only discover the relations that involve that variable. But here we are learning it in an unsupervised way, so we can learn more than just one relation. We also discovered the relation between these 3 variables and between these 2 variables. Unfortunately, or fortunately, these relations that are already known in the literature of knot theory. So the unfortunate part is that we did not discover anything new with our framework, but note that our network is just very preliminary. It's just a 1 layer. It's just a 1 layer if we ignore about the classifier in the 2nd layer. So we can hypothetically we can make it deeper to get more complicated relations. But the fortunate part is that it verifies that what we discovered with the network is something is not bullshit. It's something that makes sense, that people already know in the literature. Yeah, we also did this physics example, specifically Anderson localization. I don't want to bore you with the technical detail, but again, the goal here is try to figure out the symbolic formula of the phase transition boundary. Like in Anderson localization, you have the localization phase and extended phase, and there is a phase boundary, and we want to extract out the phase boundary, especially the symbolic formula of the phase boundary, if there exists a symbolic formula for it from the raw data. Yeah, so for this slide, I don't want to go to the detail, but the point I want to make with this slide is that the CAN network have, just like cars, you have manual mode, you have manual mode, you have automatic mode. Like if you're lazy, you can just delegate everything to CANs, and CANs will return you a symbolic formula fully automated, but that might not be correct. That might not be what you want. Uh, uh, you can do that. It can give you reasonable accuracy, but may not be fully interpretable. But if you want to have some controllability over the CAN network, where you want to be more involved, you want to have some intervention, you can still do that. You can choose to you can use the manual mode, where you just handpicked some activation functions, like some functions. Obviously, they're just quadratic, linear. You can set them to be exactly the linear or quadratic, and then you retrain the other activation functions, and you see and after retraining, you see what those activation functions would change to different form. And then this gives you some insights, like give you better evidence what the next guess you would want to make. And this is like the iterative process. Like it's sort of like you are arguing or you are debating with the CAN network. Like the CAN network is give you some or you can say debating or collaborating, just like how you interact with a human collaborator. Sometimes you debate, sometimes you collaborate. But you seem to look at the same thing from different angles. Like the CAN network is really great at decomposing high-dimensional functions into 1D functions, but those 1D functions may not be perfect, and there might be some extra subtlety. But humans are super great at identifying the symbolic stuff and also recognizing the modular structure from the CAN diagram. So yeah, so the takeaway is that you can choose to be lazy, use the automatic mode, or you can choose to be more responsible and more evolved using the manual mode. Yes. So maybe in the end, yeah, I will just finish this really quick. So people have asked why it looks like CANs can, in terms of expressive power, CANs are just MLPs, are just like secretly just MLPs. So why do we need CANs? I want to argue that from a high level philosophical level, CANs and MLPs are somewhat different. CAN is like clockwork. In a clock, PCs are customized and have clear purposes corresponding to the learnable activation functions in CANs. So for a clock, it's easy to tear it apart. It's easy to tear the pieces apart and then reassemble the pieces back together to get the clock back. But MLP is like a house made of bricks. So in MLPs, the pieces are produced in the same standard way. Like each neuron takes in some linear combinations and then do the same nonlinear transformation. But it's difficult to tear. Once you have a house built, it's difficult to tear apart the bricks and then reassemble them. So in summary, the source of complexity are different in CANs and in MLPs. The source of complexity in CANs come from the complexity of each individual object, like those 1D learnable functions. But because the functions that are 1D, no matter how complicated they are, they're 1D and they have clear purposes in some sense, they are interpretable. But the complexity of CANs come from complicated interactions of individual parts. The individual parts are simple, but the interactions, the connections between these individual parts are really complicated. I guess it's more like human brains. It's more like biology. Yeah, I don't know, but like can seem like a bit seem like more aligned with the philosophy of reductionism, where you hope that where you expect that you can decompose a complicated object into a few like interpretable individual objects. Well, in MLPs, everything is connected. The reason why MLPs function is because they have this emergent behavior or collective behavior in some sense. Yeah, just some just some interesting question people ask, are cans physical? So if we think of like the Feynman diagram as physical, then unfortunately Feynman diagrams are sort of more like MLPs, because in Feynman diagrams, like on the edges, it's just like a free flowing in space without anything interesting happen. But on the nodes where two particles or multiple particles collide, it's where interesting things happens. This is more aligned. This is probably more aligned with MLPs. But cans is like interesting thing happens on the edges, but not on the nodes. And yeah, last question. People also ask, are cans biological? Because people think that MLPs are inspired by the neurons in our brains. Are there any biological analogy? I don't know at first, but someone from Twitter wrote it that cans actually is a bit analogous to the cells in retina, where you first like each individual cell receive light, apply some nonlinear transformation to it before summing everything up. I'm not sure. You guys are the experts, so please correct me if I'm wrong here. But the argument is that, well, maybe the mechanisms of cans, like you first apply nonlinear transformation and then summing everything up, is indeed biological. But I guess that's just for fun. That's just a minor justification why we need cans, because in some sense cans are also biological. Yeah, so that's basically everything I would like to share, and I'm happy to chat more if you guys have questions.
Super interesting. Thank you. Questions?
For the last example in retina, I have some question. If the network, like CAN network, is deep enough, is it still matter if you say nonlinearity is before or after the summation?
Yeah. So I guess the key difference, well, yeah, so I guess the key difference is that in CANs, the activation functions are learnable. So I guess, yeah. But whether to put the activation functions on edges or on nodes, I don't think that might be a key, that might be the key difference. Like the learnability of activation functions give you more flexibility.
Yeah. When you're talking about this, I was thinking about that CAN is decomposing different variables, input variables. Like if you have X and Y, then CAN could decompose it, because you would have a different combination of them. But like if you have a nested function like sine x squared or exponential sine x squared, then the CAN seems not able to decompose them because they don't have these primitives.
Yes, that's exactly correct. So CAN can only discover compositionality in the sense that all the 1D functions are boring. to cans. It can just approximate it with just a one B splice. It doesn't learn any compositionality for single variables. That might be one bug, if you will, for cans. If you want to really figure out, if you really want to figure out the symbolic formulas in the data set. But like for Professor Tommaso Poggio, the author of the 1989 paper who sentenced the theorem to jail, he wrote in his paper that all the 1D functions are boring. And what's interesting is this compositional sparsity when you are dealing with multiple variables. But I guess it depends on your goal. If your goal is just to learn a function efficiently, then it's fine. But if your goal is to really understand if it's sine of exponential or exponential of sine, then we probably need to think about ways to handle this.
Yeah, thank you.
Have you thought about combining cans and NLPs given their somewhat complementary nature, or perhaps despite their complementary nature?
Yeah, that's a great question. In the I guess so we have some primitives like cans can propose this can layer, which is a new primitive, and for MLPs it has this linear layers and also the nonlinear activations, which are also primitives. I mean, these are like the building blocks, and I guess as long as they fit together, you can you can freely just combine them in ways that you want. But it's just that it's a bit hard to tell what's the advantage of combining, and because I guess there are many ways to integrate the two models, and like which way is the best, and I guess it's a case dependent. It's a case dependent question. Like it again depends on what's your application, what's your goal, something like that.